Okay, everyone, let's begin with our next topic now. So next we've got partial fractions. That's another relatively straightforward topic. Now, what are partial fractions? First of all of you know how to take LCM of two fractions, right? So if you have two fractions like this, if you were to take LCM of them, you would end up getting this after simplification. If you want to do the opposite of that and go from this one single fraction to those two fractions, this process in which you go back to those separate fractions from a single fraction, this process is known as partial fractions. Okay, it's called finding partial fractions. Now, how do you do that? For this, first of all, you need to know the concept of an identity. So if you have an equation like this, for example, 2x plus 4 equals 10, you get a solution from this that's x equals 3. Now, for any equation, you only have some specific values of x that satisfy that equation. For example, in this case, for this equation, only x equals 3 satisfy this equation. If you have a quadratic equation, you can have two solutions for that. If you have a cubic equation, you can have three solutions for that, and so on. Identity, on the other hand, is different. If, for example, if you have something like this, 2x plus 6, that's identical to 2 into x plus 3. This is something that's true for all values of x. No matter what value of x you input in this, the left-hand side and the right-hand side, they will always be equal to each other. This is called an identity because the left-hand side and the right-hand side, they're just two different ways of writing the same thing. Okay, so whatever you input on both sides will always be equal to each other. Equation is different. That's only true for some specific values of x. So what we want to do here is we want to write this single fraction as two separate fractions. But these are two different ways of writing the same thing. So they will be identical to each other. When we take LCM, what we have is in the denominator, we've got fraction here, another fraction here. When we take LCM of them, we get a single fraction in which we have a product like this, x plus 4 into 2x minus 6, right? When we want to go back, if we have 8x minus 38 over x plus 4 into 2x minus 6, what happens is we say we will get two fractions like this such that one of them will have the denominator x plus 4 and the other will have denominator 2x minus 6, right? So finding the denominators is very straightforward. We just split them like this in the two fractions, among the two fractions. The first would have x plus 4 as the denominator, second would have 2x minus 6 as the denominator. Numerator, however, is something that we don't know what it is going to be. So what we do is we follow a process like this. We say, okay, this is one fraction. We want to write it as two separate fractions. We know the first fraction is going to have this denominator, the second fraction is going to have this denominator. What about the numerators? That's what you have to find out. Now, this is the form that we use for this. We write some constant in the numerator. This constant is a, this is b. And the problem is, how do you find the values of a and b from this? Now, the process that we follow for this is, first of all, we multiply the denominator on the left side and the right side. We multiply that on the right side. Now, what happens to the first fraction when it gets multiplied by that denominator? X plus 4 and x plus 4, they get cancelled, and we're just left with 2x minus 6 from there. When the second fraction gets multiplied with this denominator, 2x minus 6 and 2x minus 6, they get cancelled, and we're left with x plus 4, that's multiplying with b here. So we, first of all, remove the fraction by multiplying this thing on the right side. Then the idea is we want to find the values of a and b. For that, we input some specific values of x that would eliminate one of these unknowns so that we can find the value of the other unknowns. Since these are identical to each other, the left-hand side and the right-hand side, we know that they are going to be true. This identity is going to be true for any value of x. So we can input any random value of x and both sides would satisfy. So we input a value of x such that if one of these variables gets eliminated, for example, what one value of x that we can do is that we can input is x equals 3, because when we put that, the first bracket, this becomes 0. So the idea is we equate each bracket that we have to 0, whatever we have inside one bracket to 0, and see what value of x we get from that. So 2x minus 6 equals 0, that gives us x equals 3. If we were to input x equals 3 in this, what happens is this whole thing is going to get eliminated. Now I've done that here. So I've done that second. X equals 3. I've input x equals 3 there. On the left side, we have to input that value of x in both sides. When we input that here, we get 8 into 3 minus 38. On the right side, we get a into 0. A into 0, that's a 0. And that just leaves us with b into 3 plus 4. And from that, we can find the value of b, which turns out to be -2. Similarly, we try to input another value of x. How can we make this bracket 0? X plus 4 equal to 0. That gives us x equals -4. So if we were to input x equals -4, what happens is b gets eliminated now because b into 0, that will become 0. And we just have a left. We input the value of x as -4 in the rest of the terms and solve that equation to find the value of a. We get the values of a and b, and that gives us the partial fractions that we were looking for. 5 over x plus 4 minus 2 over 2x minus 6. And that's our final partial fractions that we get from this. Okay, that's the process that we follow for this. Now, there are two types of fractions that we would have. One is proper fraction and the other is improper fractions. For now, we're just talking about proper fractions. We'll talk about improper later, and I'll tell you the difference between them as well. Or for now, I'll just tell you this much, that the degree of the numerator, when it's less than the degree of the denominator, that's a proper fraction. In this case, numerator is x squared, denominator is x into x into x, that's x cubed. So this is a proper fraction. So for now, we're just talking about proper fractions. How would you do this? You would say, this is the fraction for which you want to find partial fractions. You break it into three fractions like this: a over x minus 1 plus b over x minus 2 plus c over x plus 1. You multiply the denominator on the left side and the right side, and that gives you this. And then what you do is, you input some specific values of x. For example, how can you make this bracket 0? You put x equals 2. You input x equals 2. What happens is, whichever term has x minus 2, that will become 0. So these two terms get eliminated. And we're just left with b into 2 minus 1 into 2 plus 1. And that gives us the value of b. When we input 2 on the left side as well, we get an equation. We get b equal to 4 from that. Then we see what other bracket we can make 0. We can make this equal to 0 by inputting x equals -1. So we can input -1. And that eliminates these two terms. We're just left with c, and we can find the value of c from that. That's what we get from this. And similarly, we can say we have got another bracket here that we can make 0, x equals 1, input x equals 1 there. That gives you the third unknown as well, and you got your partial fractions. Okay. The three different forms that you would have for partial fractions, the example that I showed you earlier, they were in which the denominator were all linear factors. Right? They were all linear factors, this, and this. When you have a fraction like this, in which the denominator is 2 or 3 different linear factors, or whatever number of different linear factors, the partial fractions form that we get for that is this. In the numerator, you have constants. In the denominator, you've got those separate denominators, those factors one by one. The first will have 2x minus 1, the third has x plus 3, the second has x plus 3, and the third has x minus 4. We get these three fractions, and now we just follow that process that we talked about, multiply this denominator on the right side, and then simplify everything, put some values of x to solve that further. When we have repeated linear factors in the denominator, what happens in this case is, for any non-repeated linear factor that's appearing, for that we will just do a over x plus 5. But this is x minus 3 whole squared. We call this a repeated linear factor. We can think of it like this. This is x minus 3 into x minus 3. So x minus 3 is repeating here. When we have something like this, in this case, the partial fractions form that looks like this. We have one fraction in which x minus 3 is the denominator, and another fraction in which x minus 3 whole squared is the denominator. So we consider one power x minus 3 of x minus 3 in one denominator, and power 2 in the other denominator, and that is going to come in two fractions like this. Okay. Now there's a logic behind it. I'm not going to go into that right now. You can again watch the detailed videos for understanding that if you're interested. This is all that you need to know for exam. You need to remember these conditions, these forms. This is the form that you would get. Now, you won't see any example in the past papers until now, but in the recent past papers, they are trying new things. So what if you end up having a cube there? What would happen in that case? In that case, you would say this is a over 2x minus 1 plus b over x minus 5, b over x plus 5. You consider power 1 first, and you consider power 2, and then power 3 like this, right? So it's the same pattern that appears here as well. In earlier case, the power was 2, so we consider x minus 3 power 1 and x minus 3 power 2. In this case, we consider x plus 5 whole squared, x plus 5 whole cubed. All right. This is what happens when you have repeated linear factors. This is still a linear factor inside, but it's repeating. When you have a quadratic factor means you have x squared like this, not whole square, but you have a square on x. That's a quadratic factor. In case of quadratic factors, in the numerator, we consider two terms, one x term and one constant term. So in this case, we could say it's a over x minus 2 plus bx plus c over 3x squared plus 1. That's the form that we've got for this. The process will remain the same. We'll multiply this denominator on the right side. Then look at the brackets, what you can make 0, and input those values of x. We'll have a look at these examples later. But that's the idea. These are three different forms that you can have: non-repeated linear, repeated linear, quadratic factor. If all of them were to come combined, again, it hasn't happened until now, but the idea would be the same. The non-repeated linear factor, that's a over 3x plus 6. The repeated linear factor, for that you'll have two fractions, one with x minus 2 in the denominator, another with x minus 2 whole squared in the denominator. And then you have a quadratic factor, that's bx plus e over x squared plus 4. Now, sometimes you will see later on, especially in integration, you might end up getting something like this: 3 over 2x minus 1 into x squared minus 4. Now, the first factor is linear. For that, we just have a over 2x minus 1. But consider this is, have a look at this. This is a quadratic factor, as in that's what it appears to be initially. However, this is something that can be factorized further. X squared minus 4, we could write that as x plus 2 into x minus 2, so that it becomes two different linear factors. So if you had to find partial fractions for this, we would have to break it down into parts like this, first of all, to make it x plus 2 into x minus 2. And then we say this is b over x plus 2 plus c over x minus 2. For this, you cannot do bx plus c, because you cannot do bx plus c over x squared minus 4, because the idea of partial fractions is we want to break the fraction down as much as possible. This fraction can be broken down further, so that is not acceptable. You'll have to factorize this and then find the partial fractions. Again, integration later on, you'll also see expressions like these. For example, if you had 3x plus 7 divided by x squared plus 7x plus 12, and they wanted you to find partial fractions for this. Now, in the denominator, there are no factors as such. However, you can actually factorize the denominator, first of all, to write it as x plus 3 into x plus 4. And then you write the partial fractions form as a over x plus 3 plus b over x plus 4. So sometimes it is possible that the denominator is not already factorized. You first have to factorize that and then find partial fractions of that after that. Okay. Now, this is what happens in proper fractions. These are some examples of that. If you have a quadratic factor in the denominator like this, what would happen in that case? You'll say this is a over 1 plus x plus bx plus c over 1 plus 2x squared. For the quadratic factor, we have bx plus c in the numerator. Now, you multiply the denominator on the left side to the right side and see what that gives you. When you multiply the denominator on the right side, in this case, what you end up getting is a into 1 plus 2x squared here plus bx plus c whole times 1 plus x there, right? Now, you think of what brackets you can make 0 in this case. The first bracket, 1 plus 2x squared equal to 0. That does not give you any solution. So you're not getting any value of x from this. The other bracket, 1 plus x, can you make this 0? Yes, x equals minus 1. So that's what you can start with. You can say, let's input x equals minus 1 on both sides. That will eliminate this whole thing. And you can find the value of a from this. That turns out to be minus 1. Now we have run out of brackets that we can make 0. When that happens, what you should do is, since we could actually input any value of x here, inputting values of x such that the brackets became 0, that was more efficient because that eliminated some of the unknowns. But now, since we don't have any brackets that we can make 0, what we do in such cases is we try small positive values. First of all, 0, but then small positive values of x, and then we solve the equations that we get as a result of that. For example, in this case, we input x equals minus 1 initially. Now, since there's no other bracket that we can make 0, what we do is we say, let's input x equal to 0 next. Now, when we input x equals 0, what happens in this case is this is b times x here, right? So when x is 0, when x becomes 0, this gets eliminated. You already know the value for a, that's -1. You can use that here, and that will give you the value for c, which turns out to be 1, right? Because b gets eliminated in this case when we input x equal to 0. And then finally, put another value of x. You can put x equals 1. Small positive integers, they're going to be easy to calculate and save you from careless errors. X equals 1, that's the next value that you can input. Now we already know the value for a, we already know the value for c, and you'll get the value of b from that. Okay. And these are the partial fractions that we get eventually: -1/1 plus x plus 2x plus 1 divided by that. Okay. Now, what if you had something like this? So sometimes you can get fractions that have x squared in the denominator like this. Now, how do you treat this? How do you treat x squared? Is this a repeated linear factor? You could think of it like this. You could say this is x and then whole squared. So it's a repeated linear factor. That's one way of thinking about this. Another way of thinking about this could be that you say this is a quadratic factor, right? With x squared. And in that case, you would say that's ax plus b divided by x squared. You could also do that. However, although they accept this a lot of times in the marketing scene, it's better to treat this as a repeated linear, because that further splits the fractions, and ideally that's what we want. If we treat it as repeated linear like this, then the form that we would get in that case would be a over x plus b over x squared plus c over 10 minus x. Okay, and that's a better way of writing this rather than treating this as a quadratic factor. Now, if we do it this way, what happens in the next step now? We multiply this denominator on the right side and we get ax into 10 minus x plus b into this plus cx squared. Now we have to think about what brackets we can make 0. We can make this bracket 0, that's x equals 10. That gives us the value for c. And now we have run out of brackets. What do we do then? We can input x equal to 0 then. X equal to 0, when we do that, c gets eliminated in this case. And we already have the value for, in fact, we have the value for c, that doesn't matter. We input x equal to 0, and that gives us the value for b here. Then we input x equals 1, because now we've run out of brackets. We use any small positive integers, x equals 1, and that gives us the third solution. Okay, a, b, and c. And that's the factorized form that you end up getting from this. Okay, let's have a look at this example. Now, what about this? This is 7x squared minus 3x plus 2 over x into x squared plus 1. You've got a linear factor, non-repeated linear, a over x is the form that we have for that. X squared plus 1, that's a quadratic factor. For that, we have bx plus c in the numerator. Now, in this case, you see what's happening. When we multiply the denominator on the right side, this is what we end up getting on the right side. Now, can we make this bracket 0 somehow? We can't. X squared plus 1 equal to 0. That does not give us any value for x. So what do we do then? We input x equal to 0 first of all, because when this becomes 0, bx plus c, that will get eliminated. So we could start from that, input x equals 0, and that gives us the value for a. Now, in this case, when we input small positive values of x, we can input x equals 1, x equals 2. This is one case in which you end up having to solve simultaneous equations. Otherwise, this method is very efficient in 95%, 99% of the cases. This is one case in which sometimes you have to end up having to solve simultaneous equations because some variable does not get eliminated. So in this case, when you input x equals 1, you get b plus c equals 2. X equals 2, that gives you this. And you have to solve these simultaneous equations. You can do that, solve them simultaneously, find the values of b and c. Now, only in this particular case, there's an alternative that you could use. That alternative is a general method that also works in most cases. But in most cases, this is more efficient than what we're doing here. However, once it turns out that you end up having to solve simultaneous equations in some rare case like this, what you would do would be, you would say, okay, let's find whatever constants we can easily using this method first of all. So x equals 0, that gives you the value for a directly. So that's pretty straightforward to figure out. Now, once you have done that, once you have found the value for a like this, That turns out to be 2. Then you could use comparison method after this. You could say, okay, this is the expression that we've got. Let's simplify both sides. Simplify, the left-hand side is already simplified. The right-hand side, we could simplify this, and then see what is the coefficient of x squared, what is the coefficient of x, what's the constant, and then you do comparison. In this case, this would be more efficient. Compare the coefficients of x squared, that gives you the value for b. Compare the coefficients of x, that gives you the value for c, and that becomes much quicker as compared to solving that simultaneous equation. So this is what I would recommend. This is the general method that you use in every single case, inputting values of x like this. In some rare case, it doesn't happen very often, very rare, in which you end up having to solve simultaneous equations because you cannot eliminate the variables. In that case, you stop at this point, and from this point onward, you do comparison instead, and that will make it a bit more efficient like this. Okay. Otherwise, in general, this is not as efficient as the other method. You will have to solve simultaneous equations and in most cases and while you're doing comparison. So it's better to use that method where we input values of x like this. All right. Okay. Now, what about improper fractions? You can have improper fractions as well. In numbers, improper fractions used to look like this. If the numerator was smaller, we used to call them proper fraction. If the numerator was bigger, we used to call them improper fractions. What about polynomials? In polynomials, first of all, you need to know what the degree of a polynomial is. Degree of a polynomial is the highest power of a polynomial in simplified form. For example, this polynomial, its highest power is 3. We say the degree is 3. This polynomial, what's the highest power? X into 2x squared. The highest power would be what we get after multiplication of x and 2x squared. In simplified form, the highest power is 3. We say that's the degree. Similarly here as well, what's the highest power in simplified form? If we were to expand this, we would have an x squared from this. We'll have an x here. We multiply them, we get x cubed. So the degree of this polynomial is 3, right? That's how we find the degree. Highest power in simplified form. Now, a proper fraction is one in which the degree of the numerator is less than the degree of the denominator. All the examples that I showed you earlier, all of them were proper fractions because in them, the degree of the numerator was less than the degree of the denominator. Now, sometimes you can have improper fractions as well. What are improper fractions? Improper fractions are fractions in which the degree of the numerator is greater than or equal to the degree of the denominator. Now, in partial fractions, you will only have to deal with one of these cases. In partial fractions, you only have to deal with this case when the degree of the numerator and the denominator, that's equal, okay? You would not have to deal with the greater than case. That will come later on in integration in some questions, but not in partial fractions directly. In partial fractions, it will always be equal, okay? For improper fractions, the degree would be equal. For example, if you have a fraction like this, x plus 3 over 2x squared plus 1 into x plus 5, the first one, the degree of the numerator is 1. For the denominator is 3. We say it's a proper fraction. For the second case, the degree of the numerator is 3. For the denominator, it's also 3. They're equal to each other. So we say it's an improper fraction. Okay. Now, for improper fractions, we would not have the same forms as before. It will be slightly different. What happens is, we have another constant in improper fractions. So you have non-repeated linear factors, we would still get those 3 fractions with those denominators separately, 2x minus 1, x plus 3, x minus 4. But we would have an additional constant with them like this. One additional constant. We'll have an a, or you can put that in the beginning or at the end, it doesn't matter. Similarly, for quadratic factors, for repeated linear factor as well, the other terms remain the same. X plus 5 is coming once, x minus 3 whole squared. However, we have an additional constant that is added here. And similarly, for quadratic factor as well, the standard form that was there before for proper fractions, that remains the same. However, you just have one additional constant added to it. So the improper fractions in the standard forms, we have an additional constant like this. Okay. There's Asan going on here. I'll explain what to do with this additional constant after that. 1 minute break and then resume after that. Okay, so in improper fractions, what we have is an additional constant in the beginning like this, or at the end, it doesn't matter. We could put that anywhere. Now, how do you find the value of this constant? Where does it come from? Basically, remember in numbers, when we have improper fractions, we could write them like this: quotient plus remainder over divisor, right? We could break them into quotient plus remainder over divisor. So that's what's happening here as well. When we have an improper fraction, what we can actually do is we can do long division, and then break it into two parts like this: quotient plus remainder over divisor. Okay. And then for this, you find the partial fractions the normal way, because then this becomes a proper fraction. And we have a constant on the side, since we will only have the case in partial fraction when the degree of the numerator and the denominator is the same, the quotient will always just be a constant. So since it's always going to be a constant, what we can do is, instead of doing that long division process, this is actually the background for this is where it comes from. But instead of doing that long division process, since we know there's just going to be a constant that's going to be added, we can add that in the standard form, and we can say whenever we have an improper fraction, we will just have an additional constant here like this. And how would we find the value of a value of this additional constant? Can be found directly. How? You would just divide the highest power term of the numerator with the highest power term of the denominator in simplified form. So x cubed, that's the highest power term of the numerator. In the denominator, what's the highest power term that you have? 2x into x into x, that's 2x cubed. You divide x cubed by 2x cubed, you get 1 over 2. So you know the value of a is going to be 1 over 2. You can just input that here, and the rest of the process remains the same. You multiply this denominator on the right side with the whole thing, including this constant. It also will be multiplied here. And then you input some values of x, as we used to do before, that can make some bracket 0, and solve that further. Similarly, in the next example here, how can we find the value for a? The coefficient of x cubed in the numerator is 2x cubed. The highest power term in the denominator, that would be x into x squared. From here, that's x squared, x cubed, sorry, 2x cubed over x cubed. The value of that constant turns out to be 2. So we don't even have to do long division process. We can find this quotient directly by just doing this division. Similarly here, this is x power 4 in the numerator, 2x raised to power 4 in the denominator. The value of a turns out to be 1/2. In this case, it's 2x cubed in the numerator, 3x cubed in the denominator, a equals 2/3. So how do you find the value of a? It's just the highest power term of the numerator divided by the highest power term of the denominator. Now, these are the forms that we brought for improper fractions. The same as before, we just have an additional constant added to those earlier forms that we had for proper fractions. Now, how would we actually do this? This is an example of that. This is an improper fraction. This is the first thing that you always have to do now. Whatever fraction you have, the first thing you do is you figure out whether it's a proper fraction or an improper fraction. In this case, the degree of the numerator is 2. For the denominator, it's also 2. Same degree, that means it's improper. So in the form that you have for this, a lot of times people end up forgetting this. You will have this additional constant here. Do not forget that. It's an improper fraction, you have an additional constant like this. And the value of that additional constant, you can find that directly as we discussed. A turns out to be 2 from this. That's 4x squared divided by x into 2x. That's 2x squared. And that gives you 2. Once you have that value of a, you can input that here. Multiply the denominator on the right side. Simplify and then just input some values of x that can make any bracket 0. In this case, I input x equals -1. That gives me the value for b. X equals 3/2. That gives me the other value, and that's it. We've got the partial fractions. Remember, when you multiply this denominator on the right side, it will also get multiplied by 2. Do not forget that. 2 will also be multiplying with that. And you get the partial fraction form for that. That looks like this. Okay. This is another example. Sometimes they give you the form like this. Again, it's an improper fraction, right? Because the degree of the numerator is 3. Degree of the denominator is also 3. They have this additional constant here. We know how to find the value of that constant. That's x cubed over x cubed. In this case, a turns out to be 1. And then we follow that same process that we did before to find the values of b, c, and d. You can have a look at this here. One last example from a recent paper. So they can have these constants here in partial fractions sometimes as well. So this is 36a squared divided by 2a plus x, 2a minus x, 5a minus 3x. Now, 5a minus 2x, they've tried to make it a bit more complicated by introducing the letters there, the letter a there. How would you do this? These are linear factors. The powers of x are all 1. So these are non-repeated linear factors. You'll have a form like this for this. And then you do it the normal way, not getting scared by that letter a. Multiply the denominator on the left side on the right side. Then you have to make these brackets 0. So 2a minus x, how can this be equal to 0? X should be equal to 2a. You input x equal to 2a, and that gives you the value for b. And then 5a minus 2x, how can that be 0? You input x equals 5/2a. That gives you another value. So I've done that here, the value for c. Then make another bracket 0. This bracket 0, that's x equals -2a. You input x equals -2a, and you get the value for a from that as well. And then you have the partial fractions from that. Make sense? Sometimes you can have something like this as well, in terms of a like this, right? The process remains exactly the same as before. You just have to be a bit more careful with the algebra because the probability of making careless errors increases here a bit. Okay, all right, let's move on. Actually, this is integration. I copied that by mistake. I will just remove that from here. And that's it. That's all that you need to know about partial fractions. We'll talk about the binomial part when we do binomial next. But as far as partial fractions is concerned, this is all that you need to know about.